For statically indeterminate beam deflection problems, this is where you have more than 3 reactions, so you can't solve for all of them with just statics. Superposition is your best friend. This should always be the first method that you try, and this is where you basically replace one of your reaction forces with just an unknown force. So then you can say that the total beam deflection is a summation, in this case of the distributed load pushing downwards and this point force pushing upwards from the middle at B. And we'll just temporarily set aside the fact that a roller joint at point C would not actually be able to hold down if B were pushing upwards, because we know that situation is not going to happen because the big distributed load pushing downwards is going to dominate, and FC in the middle is just kind of holding it up a little bit. It's not actually pushing the whole thing upwards. And now if B were actually a regular normal roller joint, this would be a much easier problem because the distributed force pushing down and the upwards force pushing up would exactly cancel each other out right at the middle because we would know deflection is 0 right at point B. But this problem is unfortunately way more evil than that because we actually have to figure out how far deflection is in the middle, right? This is an axial loading problem. First, there's a little bit of a gap that has to be filled, and then that cylinder at B is getting pushed downwards. So we actually have to get a compatibility equation for this statically indeterminate beam deflection problem that's actually an axial loading problem also. And so now looking at the cylinder in the middle, we know that the deflection is going to be that 2 millimeter gap plus delta B, however much deflection is in that cylinder. And think back a couple of weeks earlier in the course, NL over AE, that was the axial loading deflection. So now we can set this whole thing up and compare the beam to the vertical cylinder. We can say that the vertical deflection of the beam, which is deflection from the distributed load minus deflection from the point force, that deflection of the beam has to be equal to the deflection of the cylinder. So the gap plus the NL over AE. And this is the compatibility equation. And this is basically all of the engineering of the problem, right? Engineering isn't plugging in the numbers. That's the math. The engineering is formulating this complicated scenario as a math problem that can be solved. So let's start plugging in numbers. For beam deflection, I'm just going to go to my beam tables. And fortunately, in this case, we're just interested in the maximum deflection occurring right at the middle. So I can just grab the Vmax maximum deflection equation for a distributed load and also a point load that is directly in the center. So 5WL to the fourth over 384 EI. Of course, you would definitely never memorize this. You just look it up in the table whenever you need it. FL to the third over 48 EI for the point force. Again, just look it up in the table. And that's the deflection of the beam is equal to 0.0002, the gap, plus NL over AE or FL over AE for the cylinder. And I'm going to use a subscript here because this is the length of the cylinder, not the total length of the beam. So there are two different L's in this problem. But at least the E's are going to be the same since we were given that the materials are the same for both. So start plugging in numbers. We've got our 30 kilonewtons per meter. So I'm converting to 30,000 newtons. 12 meters is the length. E, 200 times 10 to the 9th Pascal. Again, units are going to be a real pain for beam deflection problems because you've got all sorts of weird units. And for I, in particular, millimeters to the fourth, right? The safest, convert everything to newtons, pascals, meters, not kilonewtons, gigapascals, millimeters. It's going to mess up the units. Make sure everything is in regular, normal units. So to go from millimeters to the fourth to meters to the fourth, we got to go 1 over 1,000 4 times. So this ends up being, instead of 875 times 10 to the 6, we're 0.000 875 because we had to move the decimal place over 12 places. And I'm going to rearrange the equation a little bit because the unknown in this equation is F. The same F that's pushing up on the beam is the same F that's causing axial loading. And so we're going to move all the F terms over to one side and keep all the number terms on the other side. So 12 meters cubed length, 48, the 200 times 10 to the 9th E, 0.000875 for I. Got to zoom out a little bit because this is such a big equation. So L for FL over AE, remember now this L is the length of the cylinder. It's how much the cylinder is stretching. So just 1 meter in the numerator. Area is just pi r squared or pi over 4 d squared. And then E is the same, 200 times 10 to the 9th. All right, a little bit of calculator work. We see 0.046 meters. This is the deflection just due to the distributed load. So that's about 4.6 centimeters or 46 millimeters of deflection based on the distributed load. Then there's the 0.002 gap. F, and plug in a bunch of calculator work here. Divide it all out, we get FB, the force in the middle, 219.8, so 220 kilonewtons is the force at B pushing upwards. We were able to solve this just using the compatibility equation, that we know the deflection down of the beam has to equal the deflection of the axial loading problem as well. So setting those two equal in a compatibility equation, 220 kilonewtons, force B, pushing up. So what the heck were we even trying to find in this problem? Let's go back to the problem statement. We're looking for the reaction forces. That's what every statically indeterminate problem is going to be. Solve for the reaction forces. So now that we have the force in the middle, we can go back and probably do what we should have done at the very beginning of the problem, draw a free body diagram to solve for the reaction forces. We can do a sum of moments about point A. That lets us find that force at C is 70.1 kilonewtons. And then a sum of forces in the y direction will show that, yeah, due to symmetry, it should be expected FA will also be 70.1 kilonewtons. Evil beam deflection problem with an axial loading problem. This is as hard as it gets for this sort of problem without going into like double integration. But superposition, that's your best friend. Always try superposition first on beam deflection problems. Going to the tables is always going to be easier than double integration or area moment method or any other method. Have a great rest of your day. Good luck on your next test.